Okay, what's the answer for this first one here? Nucleus. All right. Uh, what's the major difference that alpha and beta have over gamma? Okay, isotope. Okay, how about, that's fine. Uh, example would be easy ones would be like carbon 12 or carbon 14. Both, both obviously have 6 protons because they're carbon, but they have different numbers of neutrons indicated by the different masses. What does, oh, is that really not there? Oh, that's weird. All right. Okay, so first off, it's F20 or 20F, and that's telling you that you've got a fluorine atom with what? Anything else? $11 neutrons. And you know it's 11 neutrons because it's fluorine, so it must have 9 protons. I don't actually think we put the equations up for this, did we? Last class? We just talked about what the symbols were for wavelength and frequency, but we didn't put the equation up, did we? But it shouldn't have been hard, right? What was the equation? Or how do you calculate this? Oh, I didn't even ask you. I'm sorry. Ignore the last 15 seconds. What type of wavelength or radiation is this? It's infrared, is it? For me, the easiest thing to do is figure out what this value is in nanometers. Yeah, you're right, it is infrared. So how do I make this nanometers? This needs to be 10 to the negative 9th, right? So what would that do to 5.5? No, move it to the right. Yeah, 4 spots. Because you have to think about what does this do? It makes it smaller, right? And this makes it bigger, and so they offset each other. And that will leave it the same value as this. And so that ends up giving us 55,000 nanometers.
Oh, that's a good version.
Yeah, and the range was 400 nanometers to 750, 400 nanometers, 750 nanometers for visible light. So this guy here is longer than that. And this side of the spectrum is red, and the thing next to red is infrared, so this works out to be infrared. Blue or green, who has more energy? How do you know blue does?
Has a smaller wavelength.
How do you know without knowing what the wavelength is? Okay. It's closer to violet than green is. All right, so write all 3 types of notation with potassium with 22 neutrons. So how many protons does potassium have? We okay with 19 for potassium? Okay, so if I've got 19, then that gives me 41. So I've got K41, I've got 41K, I've got 41K19. Fill in the missing. What was the missing? Let's just do it here since we can do it right here. So what about this top one? This up here has to be 14, right? Because the mass numbers have to be the same on each side of the arrow. And so what number has to be down here as the, this has to be a 7, right? 7 plus -1 gives me 6. So then that's a nitrogen atom. And then on this other side over here, I need to add up. So this is 228 for my mass number and 88 for my proton number. And so what is that? Radium. Okay. What needs to happen for radiation to give a person cancer? What was that?
It needs to have a shorter wavelength than violet, right?
The radiation must be able to do what?
To break carbon bonds.
Needs to break a carbon-carbon bond. That takes a significant amount of energy to do that. Can it break any carbon-carbon bond? Like what happens if it breaks a carbon-carbon bond on your nail or in your hair or on the dead layer of skin surrounding your body? Has to be a DNA. So this carbon-carbon bond must be a DNA bond. And then this is happening to us all the time. Are we okay with that? When we step outside, you're getting hit with it. You're not even moving, and you have carbon-14 inside your body, and radiation is being released by your own atoms inside your own body, which can go off and destroy other atoms inside your body. But most of the time when this happens, we don't get cancer. So what usually happens when this carbon-carbon bond gets broken? So we need to think about that in two ways. So I have a carbon-carbon bond breaking during DNA, on the DNA during some kind of either mitosis or protein production. If that thing breaks, the cell might just die. The other thing that might happen is the cell does something it's not supposed to do, and what's your body do to the cell? Kills it. It's looking for things that are doing stuff that's wrong. So when you have a cell inside your body and your body notices that it's doing an incorrect thing, it kills that cell. And that's usually what happens when you get DNA mutation. Your body is like, hey, that thing messed up, just kill it. Disassemble it, put it back together in a new cell. So these three things need to happen. And that third thing, we need to make sure that either the cell doesn't die on its own or the body doesn't kill it. And only when all three of those things happen can you get cancer from radiation. You all right there, Connor?
Yeah.
No electronics? Your computer's okay? All right. And this last one down here?
That's the proton and electron, right?
Yep. It's more complicated than that, but ultimately that's what it comes down to. Does anybody know what the other piece is? Actually, we just learned. We like literally just figured out how to even find them.
In this class, or?
No, humans in general, period. We thought that they were around, but could never verify that they were. And then we built a detection facility at the bottom of a really, really deep mine filled with really, really cold, undisturbed water and put the equipment in there. No. Neutrino. We found the neutrino. So when this happens, you also get a neutrino out that, but nobody noticed it. It's very hard to detect. I'm sorry, say again?